Hello everyone, I hope you're all doing well and enjoying the INCOSE conference so far. Thank you so much for taking the time to attend my presentation today. My name is Kimberly and I'm the primary author and presenter for this paper on integrating safety analysis into model-based systems engineering for aircraft systems. This was the topic of my undergrad thesis while completing my bachelor's degree in aerospace engineering at the University of Toronto. And I had the honor of working on this topic with Thomas Robert and David Shinman, who are both system architects at Saffron Learning Systems in Canada, as well as my supervisor, Dr. Alison Oliewski. So just to give a quick overview of this presentation, I will first begin with the background where I'll be providing some definitions, and then I'll move on to explain what motivated the work that I've done. I will then talk about some of the related works found in literature before introducing the safety profile that I've created. And finally, I will end with a quick discussion on next steps. Throughout the presentation, you can also track where we are by looking at the progress bar on the top of the slide here. As I've just mentioned, I'll start by providing some background and some definitions so that we're all on the same page. As many of us at this conference have probably observed, the design of large integrated systems such as aircraft, space, railway, and automotive systems is becoming more and more complex. These systems are expected to be developed with increased functionalities while at the same time maintaining a high degree of flexibility to keep up with changing demands of customers. As a result, many companies have started to use various tools and techniques to deal with this complexity, and in addition to that, the rapid improvement of technology in recent years has also been moving us closer and closer to making Industry 4.0 a reality. As part of the shift towards using digital technology to create and manage integrated models, it has become increasingly common for companies, especially within the aerospace industry, to implement a model-based approach to systems engineering. Here's a formal definition of MBSE. So the main idea is that with MBSE, the model is the sole source of truth and is updated continuously by engineers across all disciplines as the system is developed. And by having all system-related information stored in a central repository, the interconnectedness of model elements is enhanced, which allows for an improved tracking of design change propagation, better consistency across systems, and better error identification during integration. Now, in the context of aircraft systems, safety analysis is essential. Within the System Development Process Model, as defined in the SAE Aerospace Recommended Practices 4754A, which we have here, we can see that safety analysis is an integral part of development. So, since the development process is iterative by nature, safety assessment activities are naturally expected to be performed continuously as well. As shown in this image, safety assessment begins at the conceptual design phase of the system, where preliminary safety requirements are derived. And as the design evolves throughout the development phase, the modified design must be reassessed, which often creates new safety requirements. These new requirements can then cause more design changes to occur, and hence the cycle continues up until the verification and validation activities, which ensures that the design meets the requirements. There are many techniques used to perform safety analysis, but in the context of my paper and this presentation, I'll be focusing on the generation of functional hazard assessment, FHA, fault tree analysis, FTA, and failure modes and effects analysis, FMEA. Now, in practice, safety analysis is often performed independently with different tools by safety engineers, and it occurs relatively late in the design process. In cases where the design has already been finalized before safety analysis is complete, the opportunity to influence design decisions and make the required modifications is missed. And this can be extremely costly since, according to the Systems Engineering Handbook, the removal of design faults detected during the design phase is up to 6 times more costly than it would be in the early concept phase. This multiplier can even increase to 100 at the development stage and 1000 at the production or testing stage. So with the implementation of a model-based approach to systems engineering, which is something being carried out by many companies within the aerospace industry, designs of the system change so quickly that traditional safety analysis practices cannot keep up. Typically, in order to perform safety analysis, safety engineers must first manually extract information from the system model before working on it. However, as designs tend to evolve continuously and rapidly with the help of MBSE, this results in safety analysis being performed on obsolete versions of the model and thus wasting time and money. Therefore, in order to remain consistent with the design while remaining error-free, the integration of safety analysis into MBSE is essential. Model-based safety analysis, or MBSA, provides an approach to tackle these problems by having system and safety engineers work on a common model as shown here. The system model that safety analysis is performed on can be updated in real time, which prevents work from being done on outdated information. The use of a common model also encourages safety requirements to be considered at the early conceptual design stages, which can help reduce the number of iterations and design changes further down the line. Another advantage that the use of model brings is that it allows for automation, such as the automatic generation of FTAs and FMEAs, and an increased traceability between requirements and design components. The automatic generation of these safety analysis artifacts reduces the overall development time and decreases error proneness, which enables engineers to become more efficient. However, it is also worth mentioning here that despite using a shared model in this model-based approach, the system design and safety data are still distinguishable. Now, if you look at the literature on this topic of integrating safety analysis into MBSE, the work performed can be largely grouped into two main methods. The first method is model-to-model transformation, and this is where the system model is transformed into a safety model via an external tool. However, it is important to realize that the safety model is not the same as a system model, since it is defined using a special modeling language designed for safety analysis, such as Alterica. The second method is the extension of the modeling language, and this is where a system modeling language, such as SysML, is extended to allow for the storage of safety data in the system model, which then allows for preliminary safety models to be derived directly from the system development model. Practically speaking, model-to-model transformation methodologies are simpler to implement since they make use of existing safety analysis technologies and their capabilities. So for example, Alterica models are already used for safety assessment at many major companies within the aerospace industry, and hence tools are well developed and in some cases even certified. On the other hand, the benefit of extending the modeling language profile is that it allows for both system design and safety analysis to be performed in a single tool. This removes the need to carry out model-to-model transformations from a systems engineering domain to the safety domain, and the avoidance of this process decreases the likelihood of errors resulting from the transformation process and can save a lot of time. So here's a summary of the analysis I have performed on some methodologies that are proposed in existing literature. The first two, SMF FTA and MEDSIS, are model-to-model transformation methods, and the other two fit into the extension of the modeling language category. In order to narrow the scope of this research, I also only focused on looking at methodologies that use SysML as the modeling language. And so based on the motivation and needs that I mentioned earlier, as well as looking at existing literature, I have identified some key functionalities that I believe methodologies that aim to integrate safety into MBSE should address. And that's what you see on the left here. As we can see, none of these four methodologies manage to satisfy all these functionalities, and so this is the gap that I am trying to address with my work. I'd also like to highlight two functionalities. The first is the capture of requirements, which ideally should be an active traceability between requirements and model elements. So in practice, within the aerospace industry, the management of system requirements is typically done using requirements modules, and these are often stored in a separate requirements management tool such as DAWs. Here, the two dashed ticks indicate that the methods do consider capturing requirements. However, its approach is not ideal. So both methods propose that requirements are stored as static text within the model, which means that there's no traceability between the textual requirements in the model and the requirements modules. And this means that any modifications to requirements in the model are not reflected in the modules and would require manual tracing every time, and this can lead to inconsistencies. The second functionality I want to highlight is the generation of the functional hazard assessment documents. This is one of the first steps in the safety assessment process. However, interestingly, none of the methods specifically address it. So as a result of all this analysis that I've just mentioned, this has led me to come up with 3 objectives that I have set out to accomplish with my proposed methodology. The first is the automatic generation of FHA, FMEA, and FTA. The second is the propagation of manual edits in the generated safety analysis artifacts back into the shared model. And the third is the traceability of safety model elements to requirements. Here's a quick overview of the method I've proposed. I will first walk through the basic idea and then go into more detail in the following slides. So of the 2 categories I mentioned previously, which are model-to-model transformation and modeling language extension, I've chosen to go with the latter. And so the key element of this approach is the extension of the SysML modeling profile. This allows all the relevant safety data to be stored together with the system model in what is called the architectural model here. And ideally, the architectural model and the requirements modules will also need to be hosted on a common platform so that the requirements can be directly linked to the relevant model element, which makes it easier to manage and trace compliance and for modifications made in either tool to be automatically reflected. As I've hinted to earlier, during the design phase, it is crucial that safety analysis is performed on the latest version of the system design. It is also equally as important that the analysis results, along with any newly generated safety requirements, are incorporated back into the design. So to facilitate this, I have introduced a safety application, which has the ability to access, change, add to, and delete model elements in the architectural model through an API. The safety application is designed to be capable of automatically generating various safety analysis artifacts using the safety data extracted from the model. And similarly, changes made by safety engineers to these documents can then be propagated back into the model via the API without them having to edit the model itself. Any type of modification will need to first pass through the application, and therefore changes can also be tracked easily. Now I will expand on the profile extension portion of the methodology. I have introduced 5 new stereotypes: system, component, function, failure condition, and failure mode, and these will be used to capture safety information that goes into the FHA and FMEA documents. I've also created a new behavior diagram called a fault tree diagram for the purpose of storing FTAs within the system model, and 3 new states: nominal, degraded, and failed, which are introduced to allow for dysfunctional behavior to be modeled in state machine diagrams. So once again, the goal of these newly introduced profile elements is to allow for the capture of safety data within the system model and to support automatic generation of aircraft level and system level FHA, FMEA, and FTAs. However, since safety certification must still be carried out independently as per aerospace standards, the generated safety analysis artifacts would only act as a preliminary document and would still need to be verified by safety experts. The diagram we see here is an overview of the relationships between the new safety elements I have created, and the key specifications represented by this diagram are that a system can have functions, failure conditions, failure modes, and states. A system can be composed of components, and each component can have functions, failure modes, and a failure effect code. Each failure condition or failure mode is allocated to a function, and each failure condition or mode also has an association link to a state. And finally, there are 3 types of states: nominal, degraded, and failed. Now I'm going to briefly go through how this safety profile is specified. So by using the contents of a standardized FHA table shown in ARP 4761, The column headings were used as a basis for the extension of the profile in order to ensure that the generated FHA would satisfy industry standards. So for each use case or function of interest, the information needed to populate each row of the FHA can be extracted from the failure conditions allocated to it. Subconditions can also be modeled and extracted with the derivation link. The attributes within the failure condition property can then be used to populate the rest of the table. And so, for example, the flight phase and failure classification entries in columns 3 and 5 here are limited to a certain number of options, and therefore I've used enumerations for these attributes. This helps to enforce consistency in how the table is populated, and depending on the system of interest being modeled, more specific phases can be included in addition to what is shown here. Now, as the failure effect is generated from a specific failure condition, the failure effect property is connected with a generates link. And finally, to provide verification evidence, the failure condition is verified by a fault tree diagram. Similarly, here's a metamodel for the generation of FMEAs, which was also designed by referring to the information required for a standard FMEA table. Even though only the functional FMEA is shown in this slide, the failure mode stereotype has been created such that it can store all the relevant information needed to produce both functional and piece part FMEAs. As I've mentioned previously, there are 3 types of states: nominal, degraded, and failed. And by introducing an association link between a failure mode and state, the state that the system enters when the failure mode occurs can be traced and represented within a state machine diagram for dysfunctional analysis. Now, for the generation of fault trees, my proposed method is to use the safety application, which is written using an API, to access, extract, and manipulate model elements. With this capability, a fault tree diagram can be populated using extracted information from the internal block diagram of the system or component that the top-level event or function belongs to. The idea behind this is to start from the output and work backwards towards the input. For example, if we take the 2 simplest failure cases into consideration, an internal part fault and an input fault. Translating this to a fault tree graph means that for a certain output fault, the fault can be caused by either an internal failure of the component or an input error to the component. For an internal block diagram that has redundant components, an AND logic gate can be used to represent that all redundant components must fail for the next component to fail. And by using this logic, a simple internal block diagram with entry, exit, and redundant components, like what is shown on the left here, will result in the corresponding fault tree as shown on the right. So to summarize, for a given failure mode or condition, which serves as the top event of the fault tree, the idea is that the safety application can identify the system or component that it belongs to and find the internal block diagram of that system or component. And starting from the output port of the diagram, the application can be coded to navigate through the diagram towards the input port and populate the fault tree diagram with the possible failure events using AND and OR logic gates. Now, to address the final objective of tracing requirements to safety elements, the proposed profile extension also introduces a direct connection between safety requirements and model elements. Here, the satisfied link can be created between a safety requirement and any model element, since there are many ways in which a requirement can be satisfied. For example, it could be by simply adding a component to the design. It could be by proving that a failure mode has a certain failure effect, or just by specifying if a failure condition has a certain classification. In addition to that, to account for possibilities where safety requirements are developed or updated as a result of either safety or model analysis, the profile also allows for derivation relationships from a requirement to any model element. As you might recall, in my proposed methodology, the requirements module and architectural model should be both hosted on a common platform. This allows for requirements to be directly loaded into the architectural model and ensures that they are automatically updated if any modifications are made. And hence, this achieves the objective of having an active traceability link between model elements and safety requirements. In summary, The proposed methodology consists of two key parts. The first is an extension of the SysML profile to include safety data, and the second is the introduction of the safety application. With the introduction of the extended profile, safety-relevant properties can be stored within the model, and hence, system and safety engineers can work from a shared model. The safety application then pulls data from this shared model in real time and automatically generates FHAs, FMEAs, and FTAs. By using an API, manual edits to these safety analysis artifacts can be easily propagated back into the model, which helps to maintain consistency between the two domains. I also want to mention that even though tables can be generated directly in many modeling tools, I've chosen for all these artifacts to be generated through the safety application in order to maintain consistency and in consideration of user experience. That way, safety engineers will only need to pull information from one platform instead of through multiple sources. To conclude, here are some next steps or opportunities for future work that I believe would be very interesting, but unfortunately was unable to address within the time constraints of my undergraduate thesis. I don't imagine there to be any particular order to this, but next steps would definitely include doing further research into the exact implementation methods needed, since what I presented and outlined in my paper have only been described at a high level. Another next step would be doing a case study or proof of concept to see if this proposed method can be put into practice effectively, and working on expanding the capabilities of fault tree generation to deal with more complex logic gates. And finally, what I believe is the most important at this current stage is to work with stakeholders and industry experts to obtain feedback on what I have proposed and work together to see how it can be improved. And just to give a quick preview of what I'm currently working on, so I'm in the middle of a 2-year master's degree program at the University of Toronto right now, and I'm actually working on extending part of the work that I've presented here today. My current research focus is on the automatic generation of aircraft and system-level FHAs from the architectural model, and I'm using IBM engineering lifecycle management tools in order to perform this. As part of my research, I'm continuing my work with the experts from Safran Landing Systems to ensure that the work that I do is grounded by industry needs. So hopefully, if all goes well, I will be able to present my work again and provide an update during the next INCOSE conference. So this brings me to the end of my presentation. Thank you all very much for listening, and I would be happy to answer any questions you might have. You can also email me at this email address here on the slide, and I'd be happy to connect and discuss any similar topics.